Hi everyone, thanks for still being here. We all know that today's accelerators are everywhere and they are a key part of modern systems because they can dramatically speed up applications from machine learning to video processing. But that speed up comes with hidden costs, basically security risks. So how do we know that we could safely use them in a system without exposing more problems? So this isn't just a theoretical problem. It can lead to serious breaches like privacy or data corruption. So let's break down a little bit. In a traditional system, the CPU accesses memory through interconnects, so fairly straightforward. But when we add accelerators to the system, it also becomes a master on the interconnects with direct access to the memory. So here's the problem. Unlike CPUs, the accelerators often lack robust security measures. That means any memory accessible to them is at risk and vulnerable to unauthorized read or stores or writes. So let me show you what I mean. So imagine someone is running an application that decodes video using an accelerator. And it's accessing the video data in a DRAM. Now suppose a malicious actor comes along. They run a second seemingly harmless application on another accelerator at the same time. And they try to access the memory. So here is the scary bit. So the second application might be able to snoop on or even override data being processed by the video decoder. So there are software-based solutions out there, such as Capsicum, which deeply depending on the operating system, but they often involve complex implementations. So this means high overhead and limited scalability. In the meantime, hardware solutions are compelling because they offer lightweight add-on components. They're always on, require minimal software changes, and can protect memory from unauthorized memory access proactively. So what do we have already in the hardware security world? One of the most well-known and influential architectures is CHERI, which stands for Capability Hardware Enhanced Risk Instructions. It introduced a new way to manage memory accesses using something called capabilities. So instead of using plain pointers like in traditional systems, CHERI uses fat pointers. So these are pointers that carry extra metadata. This includes capability tags that validates whether the capability information is valid or not. So, and what permission the pointer has. So read, write, or execute. What type of the object is pointing to, and the memory bounds. So it cannot strain into any other regions. So even if a program has a bug or is under attack, it cannot access memory it shouldn't. This significantly reduces the risk of memory-based exploits. While CHERI is a very powerful step forward for CPU security, it is not a complete solution, especially when it comes to accelerators. So here is an issue. When we introduce an accelerator into CHERI-based systems, particularly in embedded systems where CPU and accelerator share memory, we can actually see that the accelerators can break the protection model. Why? Because the accelerator often bypasses CHERI capability checks. It can directly access user data in memory. Sometimes even worse, it could corrupt existing capabilities, the very thing that CHERI relies on for memory safety. And this is a serious vulnerability. It means that malicious user could potentially just completely bypass CHERI and simply by exploiting accelerator to perform unauthorized memory access. So even with CHERI in place, the system is still at risk. So what do we have today? In most large-scale systems, we rely on MMUs, which stand for Input-Output Memory Management Units, to isolate memory accesses from accelerators. But there is a problem. MMUs operate at the page level, typically 4 kilobytes or larger. So this means they offer coarse-grained protection, which isn't effective for small memory buffers, like those used in many accelerator workloads. So while helpful, MMUs are not precise enough for fine-grained memory safety. On the other hand, some recent efforts have been looking into embedding capabilities directly into accelerators. So one notable example is the SNPU paper from last year's ISCA conference. But still, these approaches are architecture specific, meaning that they need to be custom built for each accelerator design, which are quite complex to implement and verify, and often requiring substantial hardware redesign and engineering efforts for secure accelerator integration. And there is another or even critical issue. So accelerator and CPUs may not end up speaking different security policies. And there are also accelerators that are not well protected in the system. And this mismatch can create gaps in the protection, leading to new unintended vulnerabilities in the system. So clearly, while progress is being made, but we still need a better unified solution for secure accelerator integration. So our work aims to tackle two key challenges in memory safety for heterogeneous systems. So protection granularity and heterogeneity. So we seek a fine-grained solution, and it should be adaptive to most heterogeneous systems without changing of accelerators. So we propose CapChecker, a lightweight add-on architecture that guards memory accesses from accelerators using CHERI capabilities. So this ensures both CPU and accelerators speak the same policy, effectively achieving system-level protection. The actual implementation is like this, but the details can be found in the paper. As this is the first work extending CHERI beyond CPUs, here we make three assumptions. First, the CPU is already protected by CHERI, as is a CHERI-based systems. No dynamic memory management on accelerators, and we assume software components are trustworthy. So how does the protection model look like? We now introduce a capability model for heterogeneous systems. Here is the reachable address space by the system. The operating system holds the capability root to guard accesses of different objects. The operating system initiates a few applications on the CPU with exclusive memory addresses and execute in parallel. These CPU tasks may initialize subtasks and allocate data buffers during the compute, but they are within the address space of their parent task. The CHERI capability ensures that a CPU cannot access a memory region that it should not. For example, if task 2 tries to read the data stored in buffer A, the request will be blocked and trigger an exception. And we now show how to extend this to this traditional capability model for CPUs to accelerators. Like CPU tasks, accelerators are initialized with their own address spaces, but they can only be initialized by a CPU task as parents. The CPU task should also allocate buffers that are computed by its child accelerator tasks, as we already assume that the accelerator cannot do dynamic memory management. However, this still works for most cases, as accelerators have capabilities to access these allocated buffers vertically, and will compute with them through DMA. So for example, if accelerator task 1 cannot access data stored in the buffer D because of the CHERI capability, and also cannot access the data allocated exclusive to a CPU task. So this ensures that the accelerator tasks are safely wrapped up in a CHERI capability model and cannot go out of the box. They work with existing CHERI capability without modifying anything on the CPU side. And we now illustrate a high-level overview of our CapChecker hardware design. So the key component in the capability is a capability table that holds a set of CHERI capabilities created by the CPU. So the capabilities are read-only for accelerators, as they cannot do any dynamic memory management. So for each memory access, the relevant IDs are used to identify which objects that are fed into the table to fetch the corresponding capability. And after decoding the CHERI capability, they are able to use to check if the request memory access is valid. So this includes permission checks and bounds checks. If it passes the check, the request will be forwarded to the interconnects and proceed. If the memory access is unauthorized, then an exception flag is set in the control register to inform the CPU and also update the capability table. This provides a lightweight memory guard for accelerators, and is independent from their hardware architectures. So how do this capability managed in the cap checker table? So we rely on software drivers to allocate the free capabilities for accelerated tasks. When a buffer is to be allocated, the relevant constraints include data, task ID, pointer ID, and the capabilities are passed to the cap checker. So it will check the tag of the capabilities to see if this is valid. If not, and the error will be triggered. And then the driver will try to look for empty lines in the cap table. If there is, if the whole cap table is full, it will just stall waiting for a new line to be available. Once the new line is found, it will just allocate the capabilities in the table. Similarly, when we try to inject a capability, it will first check whether the tag is valid, and then also look for whether the target's capabilities exist in the cap table. If not, we will report it to the CPU. Otherwise, we just inject that from the cap table. Great. So how good is it? So our evaluation mainly focused on two aspects, security and performance overhead. So first, we evaluate our work on CWE classification for security analysis, and we compared it with related work, MMUs and SNPU. So here we only highlight the key points. The cap checker achieves the finest protection granularity for traditional unauthorized memory accesses, such as buffer overflows. So as I mentioned before, MMUs compartmentalize data between pages. So and SNPUs, they only protect data between tasks. There are special cases, as we assume that software components are trustworthy. So MMU has two limitations, because it requires updating data structures to synchronize the use of target pointers. So imagine you have a pointer that's points to another pointer, then it will require significant engineer efforts to implement the software driver to trace the pointer tree to restore or invoke this pointer data structure. While SNPU and cap checker implement this, especially for cap checker, like the CHERI capability already implement that at get it by nature. So these two techniques support that. For the unstructured pointer dereferences is about the forgeability of the capabilities. So although CHERI capabilities provide unforgeable pointers on the CPU, so accelerators, the cap checker also contain the tag and capabilities that could dereference a pointer, could not dereference a pointer that's forged by the input outputs. And MMU doesn't have these capability checks. So there are more security analysis in the paper, and I'm also open to discuss them after talk. Another key metric is the performance overhead. There are more experiment results for other benchmarks, but you could find them in the paper. But here, let's just zoom in to see one specific benchmark. But the key thing we observed from the bar chart is that we have different configurations, like normal CPU, and then we also have like CHERI-based CPU with a little bit of performance overhead. And then once we add accelerator into the system, we could observe significant speed up because accelerator explores data parallelism. But this doesn't mean that the system is safe. So we evaluate the CHERI-based accelerator or CHERI-based CPU plus cap checker and accelerator, and evaluate the overhead compared to vanilla CPU plus accelerator. And we find the overhead is within 0.01% for this benchmark. The key takeaway here is that we observe the performance overhead of CHERI on accelerators are significantly smaller than overhead on CPUs because the data pipeline. On average, the cap checker has performance overhead within 5%. In conclusion, cap checker achieves compartmentalization for heterogeneous system via CHERI, and it's fine-grained compared to existing approaches. Our solution is accelerator independent and can be applied to many existing heterogeneous systems. Our future work plans to further improve the memory safety by supporting dynamic memory management on accelerators, and also reducing system overhead by microarchitecture exploration of the cap checker. Thanks. I'm now taking questions.